We're going to look at Legendre polynomials, which are polynomials, solutions of this equation, 1 minus x squared y double prime minus 2xy prime plus k times k plus 1y equals 0. Now, k can be any positive integer or 0. And for each of those, we get a separate equation and a separate solutions. Actually, we get two solutions. One of those solutions is going to be a polynomial of length k. That is, it's going to highest power is going to be x to the k. The other solution is going to continue indefinitely, and we're not going to be that interested in those. Now, first, of course, what we're going to do is set y equal to the sum n equals 0 to infinity a sub n x sub n. And we're going to plug that into this equation. In order to do that, of course, we'll need y prime, which is the sum n equals 1 to infinity n a sub n x to the n minus 1. And we'll need y double prime, which of course is the sum n equals 2 to infinity n times n minus 1 a sub n x to the n minus 2. Okay, if we plug all that in there, we're actually going to have, instead of three terms, we actually have 4 terms because we're going to multiply y double prime times 1 and y double prime times minus x squared. So we get the following set of equations. We get the sum n equals 2 to infinity n times n minus 1 a sub n x to the n minus 2. That's from the y double prime times 1 minus the sum n equals 2 to infinity n times n minus 1 a sub n x to the n, because x squared times n minus 2 is, of course, x to the n. And then something similar happens with the y prime term. We're going to have n a sub n x to the n minus 1, but we multiply by x, we're going to get x to the n. So we're going to have minus 2 n a sub n x to the n. And then, of course, we have just the k times k plus 1 a n x to the n. All that, of course, equals 0. Okay, now all these terms have x to the n except the very first one. So we're going to change that very first one. We're going to let I equals n minus 2. We're just looking at that first term, and therefore equals I plus 2. This is a change of index, so I'm going to get everything in terms of x to the n, and then I can factor out the coefficient. Okay, and when we do that, that very first term is going to become the sum. You'll notice when n equals 2, I equals 0. And then n equals I plus 2, so we have I plus 2, I plus 1, a to the I plus 2, x to the I. And then we have these other terms, equals 0. Now what we're going to do with this term is, because I is just a dummy index, we can now replace the I with the n, and then it'll make it all look the same. So finally, we're going to replace the I with the n, and then we're going to rewrite these and see what we have. And we're going to have the sum n equals 0 to infinity of n plus 2, n plus 1, a to the n plus 2, x to the n, because we're going to substitute I, we're going to make it n now, minus the sum n equals 2 to infinity and n minus 1 a sub n x to the n minus 2 times the sum n equals 1 to infinity and a sub n x to the n plus k times k plus 1 times the sum n equals 0 to infinity, an x to the n, all that equals 0. Now we can factor out the x to the n. So for n greater than 2, all of these are the same. We'll deal with the n equals 1 and n equals 0 case in a minute. So for n greater than or equal to 2, we're going to have one master sum. N equals 2 to infinity. And each of these has an x to the n, which we're going to factor out. And we're going to have n plus 2 times n plus 1, a to the n plus 2, minus n times n minus 1, a to the n, minus 2, a sub n, a to the n, plus k times k plus 1, a to the n, all times x to the n. All of that equals 0. Now this is very interesting. So now we have an expression where the coefficient of x to the n is this kind of complicated thing. And in order for this polynomial to be 0, each of the coefficients has to be 0. I made a mistake here. This should be n. So collecting all those terms for n greater than 2, we have a master sum. And that sum looks like n plus 2 times n plus 1, a to the n plus 2, minus n times n minus 1, a to the n, minus 2n, a to the n, plus k times k plus 1, a to the n, all times x to the n equals 0. Now this is a polynomial in x to the n for each n, and therefore the coefficients of x to the n has to equal 0. So we have the following condition for n greater than or equal to 2, n plus 2 times n plus 1, a to the n plus 2. Now I'm going to factor out the a sub n, plus minus n times n minus 1, minus 2n, plus k times k plus 1, a sub n equals 0. This is a so-called recursion relation. It says if you give me a sub n, I can get a sub n plus 2. If you give me a sub n plus 2, of course, I can get a sub n plus 4. Let's solve this for a sub n plus 2 in terms of a sub n. So finally, we have a sub n plus 2 equals n times n minus 1 minus 2n minus k times k plus 1, all that times a sub n over n plus 2 times n plus 1. Now, let's take a look at this expression up here and simplify that just a little bit. We would have n squared minus n plus 2n when we bring it over, minus k times k plus 1. I made a sign mistake. When I brought it to the other side, I have to change that sign. So we finally get a sub n plus 2. Now this is n, this becomes n squared minus n plus 2n, so it becomes n squared plus n. So the whole thing becomes n squared plus n minus, let's multiply this out, minus k squared plus k. This is a very interesting relationship because k is going to be an integer. And when n hits that integer, this numerator is going to be 0. And therefore, an plus 2 is going to be 0. And then an plus 4 is going to be 0, etc. So all the an's after that are going to be 0. Let's go back and deal with the case n equals 0 and n equals 1. For n equals 0, we have